Okay, I think we'll get started. We also have quite a few folks online. So for those of you who are online, you can type in your questions. We'll have someone here.
You tested earlier, it sounded great, but now we're not hearing it.
You're not hearing me at all?
Not really.
Oh. You can't hear me, Jeff.
Barely.
Really? Because it's so loud over here. All right, well, I can use the mic. I mean, you can give me the mic if they can't hear me. All right. All right, now you can hear me, right? Yeah, I don't think I could have spoken louder. All right, so thank you for being here for today's grand rounds. We're super honored and excited to have Dr. Nicholas Christakis with us. Dr. Christakis is a social scientist and a physician at Yale University. He's really one of the foremost researchers on social networks. He directs the Human Nature Lab and is the co-director of the Yale Institute for Network Science. He's also the Sterling Professor of Social Natural Science in departments of sociology, medicine, ecology, evolutionary biology, biomedical engineering, as well as the School of Management. Dr. Christakis received his MD and MPH from Harvard and his PhD from UPenn. He was elected to the National Academy of Medicine in 2006, the American Association for the Advancement of Science in 2016, and the American Academy of Arts and Science in 2017. He studies network science, biosocial science, behavior genetics, among many other related topics. This year, this academic year, we're doing a whole series on social networks. We're just so honored to have Dr. Christakis to be able to come here and share with us his research, his latest thinking on where this field is going. So without further ado, Dr. Christakis.
Thank you so much. Thank you. Thank you very much. Can you hear me all right in the back? It's all right. And online, they can hear me all right? We're good to go? And the people in the waiting room have been let in, the 15 people? Yeah? All right. So thank you for that introduction, and thank you for having me. Humans are embedded in social networks, and these networks obey very particular mathematical, psychological, sociological, and biological rules. And understanding these rules and these principles gives us new insights into human interconnection and great opportunities to intervene in our behaviors and to change them. We can use an understanding of social network structure and function for good, to intervene in both online and offline networks in order to enhance our health and well-being. And in the broadest sense, taking the embeddedness of human beings within social networks seriously shifts our focus to the externalities of the interventions that we deliver to populations, engaging us in an understanding not so much of the response to treatment among the treated, but the response to treatment among the untreated. When we do something in a community and deliver the interventions to some people, okay, fine, what happens to them? But of greater interest to me is what happens to everyone else in the community, even though they are not the ones to whom we have delivered a particular intervention. So I'm interested in real social networks, the kind we humans have been making and embedding ourselves in for tens of thousands of years. And real social networks look like this. Every dot is a person. Every line between the dots represents a relationship between two people. Who's friend, whose spouse, whose sibling, whose coworker, for example. And to my eye, social networks are intricate things of beauty. And they are so elaborate and so complex and so ubiquitous, in fact, and have such a particular and regular topological architecture. The mathematical pattern of these networks is so similar around the world and in settings wherever they are mapped, that this regularity and this ubiquity begs the question of whether it is the case that the structure and function of human social networks is not a coincidence and rather has been shaped by our evolutionary heritage. And in a completely different line of work I'm not going to be presenting today, we've explored the evolutionary origins and the genetic underpinnings of human sociality. How and why do we have friends, for example? We, like other animals, mate with each other, but we do something that's extremely rare in the animal kingdom. We befriend each other. We form long-term, non-reproductive unions to unrelated conspecifics. We do it, certain other primates do it, elephants do it, and certain cetacean species do it. So it's a really unusual thing that our species does, makes these networks that's been shaped by our evolutionary past. I'm not going to be discussing that today, except to say that it's that past that gives this architecture in which we all live. You can't escape this any more than you can escape having a kidney or a retina that works the way that it does. So humans evolved to have social networks with particular structures which underlie all of the communications technology, all of the social learning, all of the kind of preservation of culture that we develop and that is so relevant to many public health interventions. Now, by way of preliminary background, social networks afford the people within them very different possible structural positions. I'm just going to show you one slide about this, just to illustrate some basic ideas about networks that are going to become relevant throughout the rest of this talk. So once again, this is a real network of people. Every dot's a person. The lines represent friendships in this case. And there are three basic mathematical ways that you can quantify the location of a person within this social network. For example, if you look at node B in the upper left and node D on the far right, you can see that they have a difference in that B has 4 friends and D has 6 friends, okay? This is known as the degree of a node. And most people know this about themselves. You have 10 friends. You have 6 friends. I have no friends. People know this about themselves, okay? But in addition, you can look at now, for example, nodes C and D, C in the middle, D on the periphery there. They both have 6 friends, but we with this bird's eye view, and that might be the limit of their understanding of where they are in the social network, but we with a bird's eye view can see that C and D are very different. And I can cultivate that intuition in you by asking you, who would you rather be if a deadly germ was spreading through the network? Would you rather be C or D? Ebola is spreading from person to person. Who do you want to be, C or D? D, right? D is on the edge of the network. They're going to be less likely to get it, or if they get it, they're going to get it later in the course of the epidemic. Whereas C is in the middle of the network. Many paths reach C. This is known as the centrality of a node, and it can be quantified mathematically in a variety of ways as well. By the way, who would you rather be if a juicy piece of gossip were spreading through the network? C, okay? And finally, if you look at nodes A and B, they both have 4 connections, but the difference between the two is that A's friends are friends of each other, whereas B's friends are not friends with each other. So even though they have the same degree, they have different, what is known as transitivity. The probability that your friends are friends with each other varies across individuals. So those are just a quick little background. There are many more complicated ways that you could quantify where people are in the networks. Those are 3 basic ways, 3 terms: degree, centrality, and transitivity that I'll return to later on in my remarks today. Now, in another broad early body of work using both observational and experimental methods, which I won't be discussing in detail today because I'd like to move to our more recent experimental field trials, using both observational and experimental methods, we and others have provided evidence that a variety of behaviors and other phenomena beyond germs spread within our networks, beyond just dyadic connections, via processes of social contagion. So I give something to you, you give it to him, he gives it to her, a kind of social contagion process. And we've shown that obesity, smoking, drinking, and drug use behavior can spread. And happiness, loneliness, depression, and altruistic behavior, whether you're kind to each other, can spread. And other sorts of behaviors like crime, voting, purchasing behavior, and ideas. People's attitudes, decisions, and behaviors depend in quantifiable ways on the attitudes, decisions, and behaviors of others to whom they are directly or indirectly connected. And empirically, this influence often spreads to 3 degrees of separation. So when you, for example, quit smoking, it has in a subsequent time periods a discernible impact on your friends, and your friends' friends, for example. And a key idea, therefore, about networks is that networks magnify whatever they are seeded with. Networks magnify whatever they are seeded with. If you put something into a network, the network functions like a social magnifying glass. But networks are agnostic. They will magnify fascism and violence and fake news and Ebola. But equally, they will magnify love and kindness and happiness and ideas. But they don't just give rise to those things on their own. An external force has to impinge on the network to start the process. Once you insert something into a network, for example, you can have a network of people and there's no epidemic. You infect one person, an exogenous force infects a person. Imagine a situation in which those people had no network ties, there would be no epidemic. But if there's a network, it magnifies whatever it is seeded with. And then you get an epidemic, you get many more cases because of a network. This is one of the most intrinsic properties of networks, this magnification property. But it turns out it's possible to exploit this property and other fundamental observations about network structure in order to maximize our ability to induce behavior change with interventions in populations, like public health interventions, which I'll get to, by exploiting a mathematical understanding of social network structure and of the rules undergirding social contagion. Now, of course, there's a lot more going on than social contagion. For instance, in the case of obesity, which was a paper we published in 2007, several things could be happening. So we observe, for example, that as I gain weight, my friends gain weight, as my friends gain weight, their friends gain weight, and so on. One possibility is that that's due to induction, right? A kind of social contagion, a spreading process through the network. On the other hand, if we find that there are clusters of obese people or smokers within a population, it may not be that my obesity or smoking are causing your obesity or smoking. It may be that it's birds of a feather flock together, what is known as homophily. It may simply be that you and I form an attachment because we have a similar body size or similar taste in food or in exercise. So it's not my weight gain causing your weight gain. It's that we form a friendship because we resemble each other. And the last possibility is that it's neither of the foregoing, but rather a contextual factor. So maybe it's that you and I both share an exposure to a gym that makes us lose weight, or a fast food joint that makes us gain weight. Now, all three of these are typically present in any social phenomenon. Why are your children studious? Are they studious because their friends are studious and that encourages them to be studious? Do the nerdy kids preferentially hang out together? Or do they have a charismatic teacher that's making all the kids want to be studious at the same time? Why are young people using drugs? Is it because their friends are using drugs? Do the kids that are prone to drug use preferentially form attachments? Or is there some kind of exogenous force, like a pusher, that's encouraging or selling drugs to the kids? So it typically takes a variety of econometric techniques to disarticulate the extent to which each of these is present in any social phenomenon. And because it's hard to disarticulate that using observational data, beginning about 10 or 12 years ago, we began doing experiments to test these ideas. So here's one of our first experiments. In fact, I think it's our first published experiment from 2010 to isolate social contagion. In this experiment, real people were brought into the laboratory and they were given real money and they were randomly assigned to groups of 4 strangers. And they were asked to play something known as a public goods game, which is a standard economic model for collective action. So that what happened in this game is they were told, okay, if you give $1 to the group of 4, we will double that dollar and divide it amongst the 4 people, so everyone gets 50 cents. You've given $1, you only get back 50 cents, but your group has benefited by $2 for your $1 contribution. So the optimal thing is for every person to give maximally at every round, and if they do that, they double their wealth at every round. But of course, from an individual point of view, the optimal thing to do is to be selfish, to give nothing and hope that other people contribute. So they played this public goods game, and then a bell would ring and they'd be randomly assigned to new people, and then a bell would ring and they'd be randomly assigned to new people across multiple rounds, such that we were able to create simple linear networks of these individuals to test our ideas. And here's what we found in this experiment. We found that if Eleni, highlighted in red, if Eleni was kind to Lucas in period 1, Lucas was kind to Erica in period 2, Erica was kind to Jay in period 3, and Jay was kind to Brecken in period 4. This is one of the more bizarre results that come out of my lab in the last 15 years, because what I've just told you is that how Jay treats Brecken depends on how Eleni treated Lucas, even though neither Jay nor Brecken ever saw or interacted with Eleni or Lucas. How you two people treat each other depends on how you two people treat each other, even though you don't know who they are. Here shown experimentally a kind of spreading process within the network, a kind of kindness. If I'm kind to you, you're kind to her, she's kind to him, and before you know it, he's kind to her, and they have no idea it began with me. Here shown in the case of contagion of altruism, but as I'll show you shortly, with many other public health specific behaviors in the field and not just in a laboratory setting. This geodesic spread of kindness, highlighted in red, to 3 degrees of separation, now shown experimentally, not observationally, is different from the temporal persistence of kindness, highlighted in yellow. So if Eleni is kind to Lucas in period 1, Lucas learns to be kind, and he's kind to Erica in period 2, and Lysander in period 3, and Bemi in period 4, and so on. If you fold back all the extra kindness accruing in this system, for every extra dollar Eleni gives Lucas in period 1, the network magnifies whatever it is seeded with and acts like a matching grant, doubling the downstream economic benefit from that initial act. So the ripples can be added together, and it's clear that the network fosters this beneficial spreading process, or pay it forward is real. Now, to be clear, we are affected in another way by social networks. It's not just what's happening around us that matters, whether people are being kind to us or gaining weight or giving us useful tips about clean needles, for example. The actual structure of the network also matters. Think about these 2 objects. As you all learned in high school chemistry, they are both made of carbon. Connect the carbon atoms one way on the left, and you have graphite, which is soft and dark. Take the same carbon atoms and connect them another way, and you get diamond, which is hard and clear. And there are 2 key intellectual ideas here. First of all, these properties of softness and darkness and hardness and clearness are not properties of the carbon atoms, they are properties of the collection of carbon atoms. And second, which properties you get, softness or darkness or hardness or clearness, depends on how you connect the carbon atoms to each other. Connect them one way, you get one set of properties. Take the same carbon atoms and connect them another way, you get a completely different set of properties. And it's the same with human groups. You can take a group of people and connect them one way, and they are uninventive and hostile to each other and violent and spread germs rapidly and easily. Or you take the same people and connect them another way, and they are congenial and productive and resist epidemics. So it's not just the people themselves that are relevant to these behaviors. It's the actual structure of the network around them that's highly relevant to your experience and your knowledge about the world. So new properties can emerge, such as cooperation and violence and health and happiness, because of the connections, because of the ties between people, and not necessarily because of the people themselves. And so it's not just what's happening to the people around us, whether they're altruistic or happy or rich or thin, for instance. Our experience of the world also depends on the actual structure of the ties around us, near and far. Now, one of my favorite examples of this is some work done by Brian Utsi at Northwestern. Brian, many years ago, became unaccountably interested in the success or failure of Broadway musicals. And he put together a data set of 326 Broadway musicals. And some of you may not know, but these musicals might cost $500 million to produce, or $200 million. And if they're successful, they make billions of dollars. And if they are not successful, you lose all your money. So it's a very high stakes. So he looked at 326 Broadway musical production companies. And the director, the producer, the musicians, the actors, the singers, and so on. And he mapped the networks of the team of people that were making the Broadway musical. And then he computed for those teams something very similar to the transitivity that I introduced a few slides ago, except it's called the density. On the far left, you can have a little cartoon of a Broadway musical production team, a person in the middle connected to 5 others. Among those 5 people, there are 5 times 4 divided by 2, 10 possible connections, but none of them exist. So you have 0% density. 0 out of the 10 ties exist, as shown on the left-hand cartoon. In the next cartoon over, 4 of the connections exist, so 40% density. And the next cartoon after that, all 10 of the ties exist, so 100% density. Then Utsi plotted on the x-axis the density of the Broadway musical production companies for these 326 Broadway musicals, versus on the y-axis the success rate, quantified either as the amount of money the show made or as the fraction of positive reviews. And what he found was that if nobody knew each other from before at 0% density, the show was a flop. And at the other extreme, if everybody knew each other from before at 100% density, the show was a flop. The optimal productivity of these teams was achieved with middle-level density. So it's not just who the people are and what their skills and talents are. The structure of the network is relevant to the ability of this group of people to do something, in this case, produce a successful show. Okay, now that, believe it or not, in however many minutes I've been speaking, represents like 12 years of work that culminated in about 10 years ago. And then we shifted our focus to interventions. Like, what can we do with this knowledge to make the world better? How can we intervene in the world? And we began a program of research doing experiments, doing social network interventions. And there are 3 broad ways you can intervene in networks. One is manipulating connection, which is changing the structure of a network, okay? Just like the carbon example I just gave. So I could take a group of people, connect them one way. A trivial example of this might be Alcoholics Anonymous. You take a group of people who are strangers to each other, you bring them into a little room and you connect them to each other in a fully saturated graph, high density, and then maybe, there's equivocal evidence, but first now let's suppose, it's able to elicit sobriety in these people, okay? That's a connection intervention. Or you can manipulate contagion. You can say, look, it's difficult in practice to force people to interact with each other. We're just going to accept the structure of the network as it exists, but we're going to shrewdly pick injection points into the social network to inject public health interventions, hoping that they will then spread maximally, conditional on who we pick within the network to infect, let's say, with a new idea. And last, in our latest work that also involves some work on artificial intelligence, which if we have time, I'll do at the end, is what we call position interventions, which involve changing the location of people within topological architectures. A simple example of this idea is the following. Imagine you're a teacher in a classroom and you have 20 chairs in front of you and they're nailed to the ground, specifying who's connected to whom. Those chairs specify this chair is connected to those 2 chairs and that chair is connected to its neighbors, those 2 chairs, and so on. And outside of the room, you've got 20 students of differing abilities. Where should you seat the students in the chairs to maximize learning in the classroom? You got the same pattern of chairs, the same number of students, the same ability in the students, but you could put all the smart kids in front or all the smart kids in back, or you could mix them up, for example, right? And maybe depending on how you arrange them, that would affect the amount of learning that takes place in the classroom, independent of the students themselves and their own abilities. That's a position intervention, and I'll show you some of those as well. Okay. So we have developed in my laboratory software that we call Breadboard, that we've made publicly available at this URL, that allows us, that's integrated with Amazon Mechanical Turk and can be integrated with other online labor markets or intranets within firms or schools, for example. And it allows us to create temporary artificial societies of real people. So we can, and over 40,000 human beings have participated in these experiments of ours over the last 10 years. So we'll bring 1,000 people into an online laboratory. We'll, in a kind of godlike way, say, okay, you guys are going to have this pattern of connections, and you guys are going to have some other pattern of connections, or other things we'll control about you, and then do experiments to see, can we change how you act, depending, for example, on how we connect you to each other. So here's one of our first experiments using this software from 2011. And in this experiment, what we did is we brought in several hundred people and we manipulated connection in this experiment. In the bottom, we brought people in, we dropped them into a network on the far left that has a very specific mathematical pattern to the ties. It's called an Urgis-Renyi random graph with 30% tie saturation. Anyway, it's a structure of a network that is realistic for human social networks. We dropped the people, the human subjects, into this network. We gave them real money to play with again and had them play a public goods game with their neighbors. Would they be nice to their neighbors or not, to create, benefits? And they played across multiple rounds, 10 rounds that are shown here. The blue dots are the people that are generous and kind to their neighbors. The red dots are the people that are defectors, that take advantage of their neighbors. And on the far left, you can see at the beginning, about maybe, 60% or half of the dots are blue and about half are red. But across time, on the bottom panel, in what's called the fixed network structure, by the end of the experiment, everyone has turned to be a defector, except a few little blue people here on the edge, keeping civilization alive, like being nice to each other. And the reason, again, is from the high school experiment, the high school experience. If I was your high school teacher, I said, okay, you four are going to work on a science project together as a team, and I'll grade you all based on your team project. And the four of you are put into a team, and three of them are lazy as hell, and one of you is a hard worker. And now you've got two awful choices. Either you have to do all the work for everyone, and they all get A's because of your work, or cooperate, or you defect, and you say, well, to hell with these guys, they're not working. So you then also stop working and become a defector. And that's what happens in this situation here. People start out being nice, their neighbors exploit them, and they say, well, to hell with that. They stop being nice, and by the end, you have a tragedy of the commons, and everyone is a defector, and the society collapses. In a different branch of the experiment, everything was the same, except in the top branch, we also allowed people to rewire their connections. We changed the rules of connection so that at every time step, in addition to deciding whether to cooperate or defect, they decided whether to keep connections or cut connections with a small fraction of their neighbors. And in that branch of the experiment, cooperation survives. You have all the blue dots, you see? So the point is, I can take you guys and connect you one way, and you're really sweet to each other. Or I can take you same people and connect you another way, and you're mean jerks to each other, okay? And it's not in you, it's how you're connected to each other that gives rise to this cooperativity in the broader population. Now, in a subsequent experiment, we now published in 2013, we swept the parameter space of the rewiring rate. In other words, we looked at how much rewiring was allowed. And on the x-axis here is the amount of rewiring. 0% rewiring means the networks are fixed. And then 10 and 20% rewiring means there's a little bit of rewiring. And 100% of rewiring at the other extreme means every tie is up for renewal at every time step. And that's the x-axis. The y-axis shows it's a regression computed a measure of the per round cooperation rate of the subjects. And you get this parabolic shape. This is again a parabola, but it's a different parabola than the previous parabola I showed you. And what this image says is that if people are put into very rigid fixed networks, cooperation collapses. Conversely, if they are put into really fluid networks, cooperation collapses. Optimal cooperation is when there's some rigidity in the system, but not too much. And if you think about it, our social institutions often place us in the middle range. So think about the institution of marriage, for example. If you live in a society in which divorce is impossible, 0% rewiring, and your spouse is a mean jerk to you, your options are to keep being nice to this guy for the rest of your life while he abuses you, or you also become nasty, right? So the marriages collapse. Conversely, at the other extreme, if you can divorce someone in an instant, it's trivial to divorce someone. Every day you have a new spouse, right? Why would you invest in your spouse if tomorrow you're going to have a different spouse? So you want an institution that keeps the social fluidity in the middle range, makes it not trivial to change, but not impossible to change. Or think also, for example, about the home mortgage deduction and other housing policies we have. If we had a housing policy that utterly prevented people from ever leaving their neighborhoods, what happens? People don't invest in their neighborhoods because as soon as some neighbors start putting trash out or creating a horrible environment, those people also start behaving that way. Conversely, if you have a very hypermobile neighborhood and every day you have new neighbors, you also don't invest. So you want a housing policy that puts people in the middle regime where they are not permanently stuck, but it's not trivial to leave your neighborhood either, or not, so easy. Now, where am I in terms of time, given where we started? We're good.
Were you able to ask questions?
Yeah, you could actually, and the only reason I'm not stepping away from the microphone is I'm aware that I have to stand in front of here for the online people to hear.
In the previous slide, for example, I mean, you've made some approximations that I don't understand.
Yes.
The maximal seems to be the cooperation happens at beyond 70%. So it's not the middle.
Yeah. So
It's not the middle line.
Yeah.
70%.
Yeah.
And
So-
between 70 and 95% seems to be going just
Yeah.
fine. So, you're saying in the middle. No, it's not at all in the middle.
Yes.
So it's much, much geared towards more flexibility and freedom.
Yeah.
in the middle.
So I had a little note here that I wanted to read, but in the name of time, I skipped. I'm going to read it now. The important thing about this image is not so much the precise value of the rewiring rate, but rather that the relationship is not monotonic. So this is just an artificial experiment done with online subjects in a very abstract world. I don't want you to take from this that for all social situations, the optimal rewiring rate is 70%. The take-home point from this image is simply that it's parabolic. In reality, in different circumstances, the peak of the parabola will be all over the place.
I'd much rather you say that.
Yes.
Because it's much more believable.
I know. I was moving fast and
You're taking us a little bit for granted.
yes. The details are in the paper too. That's a good point. Thank you. Other questions? Come on, the dean's opened up, so you guys can follow. Yes.
In terms of this slide before. And you may not know this, but in the fixed row, number 10,
Yeah.
there are 3 people who persevere.
Yeah. Cooperators.
Yeah, what do we know why?
Well, part of it has to do.
Especially because of the bifurcation of social media and yeah, the social.
So part of it has to do with that they're connected to each other. So notice they're not 3 randomly distributed people. So they're among, for each of them, there's a higher fraction of their neighbors that are cooperators than for everyone else. And part of that in this case is abetted by the fact that they have their backs to the edge, right? And it may be the case that by chance, these 3 people started out as being more cooperative, but that's not what's driving this, because across multiple replicates and random assignment, this is the finding that we observe. So it's not to do with these particular people. Now I've been not only given permission to slow down, I've been encouraged to slow down by the dean. So I'm not going to take it for granted. I'm going to give you all the details, whether you want them or not.
I didn't say that.
I'm interpreting. Yes, exactly. Yes. Okay. So this is another experiment now. From now, we've come up to 2019 that captures some pertinent features of the challenges of sharing in networks. Now, in this game, people repeatedly choose whether to share an unused resource, for example, Wi-Fi bandwidth. The model example you might imagine is that right now you're here, your Wi-Fi is at home. Actually, you should let your neighbors use your Wi-Fi right now. It doesn't harm you at all. Let your neighbors use your Wi-Fi. Then you go home, your neighbor's gone on the night shift. Now it's their turn to reciprocate and share their Wi-Fi back with you. This is a kind of a model for many types of collective action problems, this kind of non-zero sum sharing that might take place between people. And using this scenario, we addressed how satisfied are people with their experience of sharing in a social system. So several hundred subjects in 40 groups were asked about how satisfied they were with sharing, and we manipulated the network structure. And we specifically manipulated a mathematically more interesting, more complex aspect of the structure. So I'm going to step away here now. So I don't know if the people online, they may lose me for a second. But if you look here on the far right, we have what's called the degree distribution. Both of these networks have 15 nodes and 18 edges and 18 connections. I'll step back. I need to step back. 15 nodes and 18 edges. Stop. What do you think? So everything okay? Yeah. All right. 15 nodes and 18 edges. And then there's the degree distribution, which says how many people have degree 1, 6 people have degree 1, how many people have degree 2, 3 people have degree 2, How many people have degree 3? 3 people, and so on, okay? In both of these networks, people, we have 15 nodes and 18 edges, and we have the same exact number of people with the same exact number of nodes that they're connected to. And yet you can look at this network and right away see that there's a difference in the structure. The people within the network can have no idea. I'm in a group of 15 people, you're in a group with 15 people. There are 18 connections in our group, there are 18 connections in your group. How many people have 3 connections in your group? 3. How many people have 3 connections in your group? 3. Looks the same to the people. But we, with this bird's eye view, can see that there's a difference in their structure. And that difference is known as the assortativity of the network. On the right-hand side, popular people are befriending popular people. High degree nodes are connected to high degree nodes. And on the left-hand side, it's disassortative. Popular people are connected to unpopular people, okay? Now, real human social networks are assortative, right? Popular people are connected to popular people and human beings, whereas, for example, the airport network is disassortative, right? So it's not the case that all the little airports are connected to each other and all the big airports are connected to each other. That's not the way the airport network is. There's a hub and spoke system, which is a disassortative. And it turns out that the human beings are, that the collective welfare was improved by arranging networks to form ties between people with similar degree, even without increasing or redistributing resources. So I can take you people with the amount of money in your pockets, whatever it is, and if I organize you this way, you're more happy with the society you're in than if I organize you the other way. Same people, same amount of money, every one of you is the same, but I organize you differently, and it affects your satisfaction with the ability of the team to work together. So structure matters, just like the carbon example. Okay, let me now switch to some experiments that we've been doing that are much more public healthy, involving manipulating contagion. Now, in this paradigm of experiments, imagine that you have 2 villages in the developing world. We've worked in India and Uganda and Honduras, in many places around the world. Imagine you have 2 villages and you map the networks of the villages, but the same could apply to 2 classrooms or 2 neighborhoods in a community or 2 firms, for example. You map the network. On the left-hand side, you have the untreated village that you give no intervention to. And on the right-hand side, you have the treated village, okay? And in this treated village, you pick 6 people at random to give your public health intervention to. Maternal and child health intervention, a breastfeeding intervention, a vaccine intervention, a latrine intervention, whatever it is. You pick those 6 people. And the ordinary perspective in public health is you come back a year later and you see what fraction of those 6 people responded to the intervention, the 6 yellow dots. And you might find that 3 of the 6 people responded. But that's not what I'm interested in. I'm not interested in response to treatment among the treated. I'm interested in response to treatment among the untreated. I want to know, what does everyone else in the village do when you treat those 6 people? So we come back a year later, we measure the whole village, and we find that 3 of the 6 yellow dots responded, and maybe they persuaded 3 of their friends for a total of 6 people responding in the treated village. And in the control village, maybe by secular change, 2 people have adopted the maternal and child health practice we're interested in. Well, you should now be imagining, maybe I don't have to pick 6 people at random. Maybe I can pick 6 central people who have high centrality, as I introduced in the very first slide. Now, once again, you treat these 6 people, maybe 3 of them respond, but because of where they are, they recruit 30 of their friends to respond. Same village, same intervention, same number of people treated, 10 times the effect because of how you select the initial targets for the intervention, according to their structural topological location within the network. And this then means that we can experiment with different algorithms for picking such potentially influential nodes. Because in fact, mapping a network is not always feasible, right? Especially, I got muted again, okay. And your co-authors have more co-authors than you do. So it turns out, if you go into a network and you pick 6 yellow dots at random, and then see who their friends are, and take 1 step at random in the network, you'll get to the orange dots, which visually you can see are more central. Now, I can cultivate an intuition in you about the friendship paradox in a couple of ways. One way is to ask you to imagine that there's a party host that has 100 friends who are all wallflowers and throws a party, so you have 101 people in this party. If you sampled among those people and asked them who their friends are, 100 people would nominate the party host, and in every single case, that person would have more friends than they did. Only when by chance you pick the party host would their friend have fewer friends than they did. Or if you look at this network, you should see that on the periphery of the network, at the boundary condition, all of the people on the periphery have one friend, and that friend necessarily has at least two friends, right? So for everyone on the edge, their friend has more friends than they do. Sometimes if you look at the bottom yellow dot that goes up to the orange dot, their friend has many more friends than they do. It turns out this is not just the case at the edge of the network, it's throughout the network. The reason this is fantastic is it means you can go into a village or any population, pick people at random, have them ask them who their friends are, and then treat their friends with an intervention, and you don't have to map the network at all. You can identify the orange dots without mapping the network. Now, this is very important, I believe, because this is a necessary predicate if we're going to use network methods to enhance the impact of public health interventions. Here's a quick snapshot of some of our work exploring this idea in various places around the world. This is a place where we work in Honduras, in rural Honduras. This is what it looks like. And we've created some software that allows surveyors to map networks in settings like institutions or villages or communities or whatever. We call it Trellis, and we've made it publicly available at the URL that's below. And it addresses a host of network mapping challenges, including problems presented in low literacy populations, because we can use photographs of people. So we ask people who your friend is, and then you point to the picture of your friend. And it solves some problems where names are common, what we call our Maria Hernandez problem. If you go into these villages in Honduras and you ask someone who your friend is, they'll say Maria Hernandez. Well, which Maria Hernandez? 10% of the women in this village are called Maria Hernandez. So here you start typing Maria Hernandez. It brings up the photos of the people who are Maria Hernandez. The person points to that photo and you can make the link. And in our first field trial, which was published in The Lancet in 2015, we mapped the networks of all of the adults in each of 32 villages. And then we randomly assigned these 32 whole villages, which had 5,000 people, to one of 3 different targeting algorithms, in which always 5% of the people in the village were chosen. So this third of the villages, 5% of the people were chosen at random. In this third of the villages, 5% were chosen who had the highest degree. And in this third of the villages, 5% were chosen according to the friendship nomination technique that I mentioned a moment ago. And the questions are, how do we move a whole village, not just individuals, to change their behavior? Given a budget constraint, who do we target in this population? And who creates the most externalities for behavior change? And how can we exploit this? So for example, here is how you might target nodes using 2 different targeting strategies. Here's an actual village network. And the orange dots are 5% of the people chosen at random. And the yellow dots are 5% chosen according to who had the highest degree. And you can just see structurally the different location of the orange and the yellow dots. And we had in this particular trial, we had 2 public health interventions, a clean water intervention and a multivitamin interventions. These are some results regarding the multivitamins. On the x-axis is the days since initial targeting. We were able to monitor uptake of the vitamins day by day across time in ways that are detailed in the paper. And on the y-axis is the proportion of available multivitamin tickets that were redeemed. We did this by giving people coupons they could redeem at the village store for the multivitamins. They were uniquely numbered. We know who would be given the coupons to, so we could actually track the redemption. And there's a lot going on in this experiment and a lot going on in this slide. I'm just going to highlight one result, which is that the nomination targeting in yellow dominates the other targeting strategies in this intervention. But in some ways, this 2015 paper, the citation is here, functioned as a pilot test for a much bigger project that we still haven't published, but I'm going to present to you now. Because we followed up with this, doing a very large randomized controlled trial of 30,000 people in 176 villages in the Copan region of Western Honduras, with support from the Gates Foundation, the Ministry of Health of Honduras, and the Inter-American Development Bank. We mapped the face-to-face networks of all of these people and implemented a 2-year maternal and child health intervention, complex intervention that was trying to change multiple aspects of maternal and child health behavior, diarrhea treatment, recognizing danger signs of pregnancy or post-delivery, umbilical cord care, encouraging men not to beat their pregnant wives. So we had an intervention on intimate partner violence. Multiple aspects of were in this 2-year intervention. We chose the intervention that other scientists have shown were effective. We weren't interested in showing that the intervention worked in the people to whom it was given. In fact, what we really wanted is someone else had already shown that. What we were experimenting was with a targeting algorithm. How do we pick the people that we give the intervention to make the most externalities? And so here's the design. We had 176 villages, 30,000 people. We had an 8x2 factorial design. There were 8 targeting percentages, the fraction of people in the village that were given the intervention, 0, 5, 10, 20, and so on. And 2 targeting methods. Were those people picked at random, or were they picked according to the friendship nomination technique? And 11 villages were put in each of those 16 cells. And then the interveners, who were not us, delivered the interventions to the targeted people, and we measured the outcomes in everyone, in all the villages, whether they were targeted or not. And this was our prediction of what would happen, shown on the right-hand panel. On the x-axis is the percent targeted from 0 to 100%, which is experimentally manipulated. And on the y-axis is the percent reached, or the fraction of people who adopt the practice, which caps out at 50%, because as you all know, not everyone is susceptible to every public health intervention, or frankly, every germ, right? A germ is spreading in a population, it's not going to reach 100% of the people. So that is some arbitrary number, here shown as 50%. If there were no social effect in these populations, you would have the dotted diagonal purple line. You target 100% of the people, 50% respond. You target 60% of the people, 30% respond, and so on. There would be a linear response. Target more people respond. But that's not really what we expect, is it? We expect that there will be social influence. There'll be some social effect in a classic sigmoidal function. So here at the lower end, you target 10, 20, or 30% of the people, and they don't respond. You get 0% uptake. Why is that? Because their friends haven't responded. I give you the intervention, and no one around you has adopted, so you don't adopt. The social effect, the non-adoption of your neighbors, suppresses your adoption here until you reach a critical threshold, and then you have explosive growth in adoption, or the epidemic. And now the social effect that worked against you now works for you. The threshold is lower now. Before, when 20% of your friends have adopted, it took a lot of work to persuade you. Now, when 80% of your friends have adopted, it's really easy to persuade you, right? So this is the sigmoidal shape. What we wondered was, first of all, could we document this sigmoidal shape in an experiment, which had never been done before? And second, could we shift the curve to the left by using friendship nomination, the friendship nomination strategy? These are unpublished results. I'm sorry, the design of the trial was published as shown in this citation. The results, which I'm about to show you, have not yet been published. Yes.
In global health, we have a model of reaching out to whom we call opinion.
Yes.
So the model that you're sharing with us is biased towards a quantitative perspective. There is also a qualitative perspective. Can you tell me how you take that into account?
Yes, I can.
Some people are more influential than
Yes.
others. Some people are more gregarious than others.
Yes.
Some people are more trustworthy than others. So
Some are more innovative. They're willing to try new things. Absolutely.
So I just wanted to be reassured that at least you considered that before you saw the result.
Yes. Okay. So what we're trying to do here is we are trying to have a systematic way and an easy way of identifying people who are structurally influential, not by virtue of who they are, how rich they are, whether they're the patron in the village, whether they are older or younger. It's something not dependent on their attributes, not who they are, but rather where they are in the network. So what we're doing is totally compatible with what you described. In a way, it's a different way of identifying opinion leaders. It's a way that kind of allows anyone in the community to be an opinion leader based on their structural position within the network. Now, it is the case that, for example, people who have more friends are richer, for example. So a logical question, which I think undergirds what you're asking is, well, Nicholas, maybe it should just be easier to go into villages and figure out who's rich and give it to them. Why even engage in all this mumbo jumbo? We've done some work I won't present to you that looks at the cost effectiveness, the relative benefit of using this approach as compared to an approach that requires you to ascertain information about everyone in a village. And so remember, what in principle you can do with our method is you go into a village, you pick 10% of the people at random. In fact, I'm pitching this on Greek islands, as you know. You go into a village, you pick 10% of the people at random, and then you deliver the intervention to one friend for each of those people. And you don't need to do it in anything else. You don't need to figure out how rich they are, or who thinks they're important, or anything like that. It'll work. Did I answer your question?
More or less.
More or less. It's another way. It's another way of finding influential people.
When you enter a village also, you ask 5 people, who are the opinion leaders in your village?
Yes.
It's generally very
Strong agreement. That's correct. Yes, if you want that. That's exactly right. So you could do that, and you could just try, for example, you could ask women, for example, who's trustworthy in this village on matters related to infant health. And you talk to 5 or 6 women, and they'll give you the top 4 or 5 people who that is, and you get pretty consistent results, and you could try delivering the intervention to them. Absolutely. There's nothing about our approach that's incompatible with that. And if anything, our approach kind of reinforces the wisdom of that. Okay, so our results are exactly as predicted. These are 2 curves for 2 illustrative outcomes. On the left is the acquisition of knowledge that respiratory illnesses are prevented by hand washing. And on the right is the behavior of seeking care for a pregnancy danger sign. So this is some women during the follow-up, during the 2 years, had a baby. Some of those were pregnant. Some of those women who were pregnant had a pregnancy danger sign. Did they seek care for that pregnancy danger sign? And was that rate of seeking care higher in the friendship-nominated villages than not? And the answer is yes. Okay. The curves, the light blue line is the random selection, and the orange line is basically friendship nomination is basically shifted up and to the left. Now, I can already see your dean is looking at the curves and is wondering, well, if these blue lines are kind of flat. The reason they're flat is there's a lot of noise in the data. And because of randomization, we can still be confident in our claims. And visually, you can see the curves are up and to the left, which is the main point of this slide. And again, as I mentioned, friendship nomination is a scalable technique that doesn't require network mapping or extensive questions, which is why we are using it. Now, some of you may already have thought, now wait a minute, Nicholas, you go into these villages, you ask people who their friends are, and you say, thank you very much, and then you go give their friends something of potential value. People might resent that. So we had the idea then to test a different intervention, which we call the pair targeting intervention. Instead of going into a village and asking 10% of the people to nominate their friends, and then we treat those 10% of friends, we go into a village, we pick 5% of people, have them nominate their friends, and pick the couplets of the individuals and their friends, again, for a total of 10% of people. And we call this the pair targeting algorithm. So same chart as before, the question is, could we shift the curve more to the left using pair targeting, or at least on top of the friend targeting? And we think this would be a much more acceptable intervention and even easier to implement. And we did a randomized controlled trial of this in Mumbai, India, using a 2-month-long iron deficiency, iron fortified salt intervention for iron deficiency anemia in infants and newly pregnant women. And we worked in these so-called chawls, which you can think of as villages. There are these poor residential buildings, lower income buildings in India. And we had a 2-month-long intervention in which, so we mapped the networks of the women head of households in these 50 chawls. The chawls were randomly assigned. In all the chawls, 20% of the people were chosen, 20% of the women were chosen, but they were chosen using different algorithms at random, using friendship nomination, or using the pair targeting algorithm. This slide is just some illustrative results. This paper was just published in PNAS a year ago, and there's lots of information in the paper, but there are just 3 illustrative networks here that are shown. And on the bottom, it shows the chawl size, about the same in all, 61, 66, and 59. And then the number of targets that were chosen should be about 20%. It varies across because it's an experiment, which is 12 and 13 and 8. And then the number of adopters, which is colored purple, whether they were targeted or not. So the hexagonal nodes are the people who were taught the intervention, And the purple nodes are the people who adopted the intervention, whether they were taught it or not. And what you can see is that in the random network, 12 people were targeted and 7 people adopted, some of the targetees and some not. In the friendship nomination, it was higher, 12 in the bottom row, and in the pair targeting, even higher, 21. Same chawl, same intervention, same number of people targeted, much bigger effect because you use the pair targeting method. Okay, I have one last experiment to show you, which is on a position experiment, and then I can close with some final ideas. Do I have the time for that? Yes, okay. Because my clock here is not working. So, so this intervention, this was published in Nature in 2017, but we've done more follow-on experiments, represents the manipulation of position and explores some other ideas related to artificial intelligence. And I already mentioned the classroom example as a position intervention. So we're exploring here the performance of groups that are engaged in a collective coordination task. And this is a different task than the cooperation public goods games I mentioned earlier in the talk. And one paradigm for whether people are able to work well together is what's known as the color coordination or graph coloring problem. And in this challenge, people are put into a network, or people are in a network, you guys are already in a network, and you're told, pick a color that's dissimilar from your friends. Orange, yellow, or purple here, okay? So each of you is in a network, and you have to pick a color that's dissimilar from your friends. And if you do, you get paid. Otherwise, nobody gets paid. So you're dropped into a network, you're assigned a random color, and you look around at the people next to you. For example, this guy here is orange on the far left. He's connected to one orange connection, one yellow connection. He should switch to purple, okay? If he switches to purple, he'll reduce the number of conflicts in his immediate neighborhood, all right? And everyone starts doing this. This is a 5-minute game. People start picking colors to change their colors, looking at their neighbors, trying to minimize color conflicts. On the bottom, and then I show 3 cartoon snapshots from this experimental run at 100 seconds, 105 seconds, and 245 seconds. The game lasts 300 seconds or 5 minutes. And on the x-axis here at the bottom is time, and on the y-axis is the number of color conflicts, the so-called objective function of this experiment. And what you can see is at the beginning, the red lines indicate whether or not there's a conflict between adjoining nodes. And you can see on the far left, at the beginning, there are 12 red lines. There are 12 color conflicts. And the people start switching their colors until in 105 seconds they get, and there's one color conflict, but it's not a so-called resolvable conflict. It's an unresolvable conflict, meaning that there's no move that either of these yellow dudes can make that reduces the number of conflicts in their neighborhood. If either of them switches to orange or purple, the number of conflicts will go up. So the system would seem to be trapped in a suboptimal equilibrium here. One of these people has to make a counterintuitive move, maybe increasing conflicts temporarily, which will unlock a solution, which is what happens, so that by the end, these 2 guys have switched to orange and purple, and now you get to 0 color conflicts. The computer detects that the game has been solved, the victory is declared, and the people are paid. Now, because we are sneaky, we took 4,000 people and put them into, I forgot, like 200 groups. And we experimentally replaced some of the people with bots in some of these groups. And we endowed those, we created what we call hybrid systems of humans and machines. And we endowed these people these bots with very simple artificial intelligence. Namely, we just added a little noise. So the bots, every 1.5 seconds, looked around at their immediate neighbors and then simply picked a color that had the lowest conflict with their neighbors and chose that color. In another branch of the experiment, the bots did the same thing, except 10% of the time, they just picked a random color. And in the third branch of the experiment, they did the same thing, but 30% of the time, they picked a random color. So that's the level of noise, 0, 10, and 30% shown in the columns. And then we experimentally manipulated the position of the bots. Were they randomly in the network? Were they placed in the center of the network? Or were they on the periphery of the network? And then we computed on the y-axis. So on the x-axis is time in all of the 9 panels. And on the y-axis is the survival curve. the probability that the group has not solved the coordination game. So at the outset, there were 30 groups that just had humans, shown in orange. And then we asked the question, what fraction of those 30 groups has solved the problem at every second? And you can see that at the beginning, 100% of the human groups have not solved the problem. But then as time goes by, more and more of the groups, it's a survival function, have solved the problem, so that by the end, I don't know, 66% of the human groups have solved the problem in the control arm. And then we had the experimental arm shown in the 9 purple lines. The orange line is the same in all the panels, in the 9 purple lines. And then we can show that actually when you have bots with 10% noise that have been put in the center of the network, it improves the performance of this human group. The bots help the humans to help themselves. So what we're doing in my laboratory is we're not trying to invent super smart AI to replace human cognition, like AlphaGo or AlphaFold. We're inventing dumb AI to supplement human interaction. We're exploiting the fact that humans are smart. We're exploiting the fact that they interact with each other. We're just adding some dumb bots that act like catalysts to unlock solutions that the peoples can do for themselves. And we've repeated this with many subsequent experiments. And in fact, what happens is the humans learn to play better by having the bots among them, and not just among those humans that are connected to the bots. This ability spreads. So even humans like, you're a bot, I'm a human, I learn from your little noisy behavior, but then I interact with her and I change my behavior to her. So it's not just my behavior to you that changes, the human-human behavior is changed by your bot-like behavior. And we've now been expanding this exploration to other sorts of health-relevant problems. So coordination, for example, in evacuation in the wake of disasters. So public health disasters. How do people leave a city effectively? Cooperation. How do people work well together to address toxic water or toxic air in their environment? Communication of all kinds of public health knowledge. Evacuation situations. How do you get people to flee? Navigation and sharing. All of these collective action problems can be enhanced by the thoughtful positioning of dumb bots in hybrid systems. Okay, I'm going to close with one final idea, which will take 2 minutes, and then we have some time, I think, and hope we do, for questions. So this idea has to do with what it means when we intervene in a social network, because I think such interventions provide us with a way to manipulate social capital. Now, to understand one sense of this, consider this idea. What's the point of a connected life? How does it help us as individuals and as a species? And it turns out that networks are a resource that we can all use. Networks are a kind of social capital. Now, most people, when they think about capital, think about money. But really, capital is any stock of resources that you can put to productive use. So capital is a stock, it's a reservoir of wealth, and capital is something that you can use to produce something else with. And 2 further key ideas about capital are that in order to create capital, you have to invest skill and effort, you have to know something and do something to create capital. And second, and more subtle, and in an idea that has been keeping me awake for 25 years, is that in order to create capital, you have to make changes in a substance that make it yield a higher rate of return than it otherwise would. That at its most deepest philosophical and ontological level, the capital creation process is about the transformation of the natural world of one thing into something else. That's what capital creation is. For example, a farm is a stock of capital. By investing labor and skill, you clear the woods and you get a farm, which is capable of producing things you couldn't do with a forest, like fruits and vegetables and flowers and grains, for example. So you invest skill and effort, you transform the forest into a farm, and now you have a reservoir of wealth that's a source of productive power. It's a kind of capital. Or you take this tree, you invest skill and effort, and you make it into lumber. And the lumber is more valuable than the tree because you can do things with the lumber you couldn't do with a tree. Namely, invest still more skill and effort and make it into a violin. And the violin is more valuable than the lumber because you can do things with the violin you couldn't do with the lumber, namely make music. So at each step of the way, you transform the natural world, one thing into another, you endow the transformed thing with a new productive power, which is what makes it a reservoir of wealth and a kind of capital. So capital is a change that allows a substance to act in new ways, and that is part of what makes it a store of wealth. Now, a key innovation in thinking took place in the 1960s to see people and their skills and talents as a form of human capital. So you can take this dissolute former graduate student of mine on the far left, who's a drunkard, and you can invest skill and effort and clean him up. And so now he's no longer a drunkard, and now he's able to do something. And such as you can invest still more skill and effort and give him a proper New York City education. And he is now capable of doing still more things he was not previously able to do. At each step of the way, you work on the person's mind. Like right now, I'm investing skill and effort. I'm changing the pattern of connections of the neurons in your brains, right? Hopefully. So your brains are now capable of doing something they were not previously able to do. That's what makes it a kind of human capital. All of learning, all of education is an investment in human capital. Well, just like physical capital is created by a change in the material world, and human capital is a change in persons, social capital in organizations, in schools, in companies, in villages, in communities, in our whole society, is a change in the relations among persons, a change that renders the group more productive and capable of doing things it was not previously able to do. And that is the deepest account I can give you of what social networks mean for our lives and why it is and how it is that we can use them to make the world better. Thank you. Can I have some water? Can I have a cup of water from the back right there? Just use a cup right behind you if you could just grab me a cup.
Thank you so much. I was really stimulating that. Thank you. I think we have some time, 2 minutes, yeah, for Q&A. There's questions online.
Sure. The first question is from Sheila, and the question is, have you conducted studies on the influence of networks and vaccine acceptance?
Yes, we have done studies, not experiments with vaccine acceptance, but we've done studies. We had a paper in Social Science and Medicine in India looking at clustering of vaccine acceptance for the polio vaccine. And so that's published work. It's an observational study. It shows, unsurprisingly, that vaccine acceptance and non-acceptance appear to have features consistent with social contagion. But we haven't done experiments with that. I'm sorry, one more thing. Also with vaccine acceptance, we have another paper. So there was one paper in India. We have a paper that we published. Feng Fu is the first author, using vaccine acquisition in Harvard students during the H1N1 influenza epidemic. And we were able to show that there was a contagion in getting vaccinated. So when your friends got vaccinated, it made you more likely to get vaccinated. So we have 2 papers on vaccine. And actually, let me just say one more, if I might, on that. If you think about one idea I didn't talk to you about today, is the idea that multiple things are spreading in a network at the same time. This adds a whole other layer of complexity we haven't discussed. And those things might interfere with each other. In this latter paper I just mentioned, we thought of this as what we call dueling contagions. So imagine the H1N1 flu is spreading, as we empirically studied. Your probability of being vaccinated will depend on whether your friends are vaccinated, because the vaccine behavior is spreading socially, but your probability of being vaccinated will also depend on whether your friends have the flu, because the germ is spreading through biological contagion. So your friends get infected, you're like, oh my goodness, I better go get a vaccine because the pathogen is coming. That's a biological contagion. And you might go get vaccinated because your friends are getting vaccinated. Conversely, your probability of being infected, the biological contagion, of course, depends on whether your friends are infected, but also depends on whether your friends are vaccinated. So if your friends are vaccinated, it lowers your probability. They act like a barrier. So you have this dynamic interference. You have a spreading process of a germ spreading and a spreading process of vaccine behavior spreading. And the question is, which will win, right? Will the vaccine spreading behavior outstrip the germ spreading behavior? And this can be modeled as with differential equations in a way that's described in this paper. Anyway, those are 2 papers on vaccination.
Okay, thank you, Bill Christakis. Very much appreciate your talk.
I guess it's a comment and a question. I was thinking about, the really fascinating work you're presenting, and one thing I wasn't seeing so much of though was that I think about adolescents and young people a lot, and so wondering about a couple of points, like we think about adolescence and young adulthood as like critical or sensitive periods for social interactions.
Pure effects are especially powerful.
Exactly. So how did that do you think about age in this work, or maybe you didn't have time, and what work? And
Yeah.
then also, in the work I've done in the US and Uganda, like people are familiar in the US, but adolescents like go off to college, they move around, and similarly in Uganda, people move around looking for work. So like not just peer effects, but also like mobility, how that might change in some of the models.
So we've mapped networks in Mbarara in Uganda. So we have an old project there. We did around HIV treatment, around chicken coops, giving chicken coops to influential women within the villages. And we published malaria bed nets, how malaria bed net usage can spread within networks. So we've actually done some work in Uganda, mostly observational work, candidly. So not experimental work. But coming back to your question, adolescents, we haven't worked explicitly with adolescent populations in Honduras, because girls can get pregnant early there. When we started the study, we impaneled people at the age of 12. So actually the 30,000 people had an age range from age 12 to age 93. And none of the young girls got pregnant between 12 and 13, if I remember, but by 13, they were starting to get pregnant. So we followed them forward. So that's the only tiny slip of a group of adolescents that I've ever studied in an experiment. The main reason being it's so difficult to get permission to study adolescents. So bless you for doing that. We have done some observational work using adolescents. We published a lot of papers using the Ad Health data set in the United States, looking at sleep behavior, for example. We looked at homosexual ideation. We did a study on like same-sex sexual attraction. Could that spread in human social networks? Using Ad Health. We looked at sleep. We looked at marijuana usage. So we've done observational studies using that other data set you must be familiar with that was from 110,000 people in, I forgot how many schools across the country. And so those are the papers we've done. Did I answer your question?
Yeah, sure.
I mean, I just said and in fact, you're right. So this goes back again to your dean's point a little bit, which is, you can make sort of high-level conclusatory statements about phenomena, but oftentimes the devil is in the details. So I'm here to tell you that social influence matters. It matters at every age, but the details of how it matters will vary by life stage. So that's absolutely true. I'll second that if that's the point you were making.
Yeah, and just generally, like glad to hear there's still empirical work to be done in that area. So.
Oh yeah.
So, and then my other line of work is actually about looking at adolescent capacity for research and how that's so hard. So.
Yes. Thankfully, I don't have that problem. Yes. Yes. So to be honest, I'm going to go in a little digression, sort of scientific, sort of an epistemological digression. There's an old debate in the sciences about so-called lumpers and splitters. Darwin coined this term, and different kinds of scientists. There's some scientists who try to get a general sense of the thing and like compute an average, like on average, men are taller than women, or on average, there's more biodiversity on big islands than small islands, right? Those are the lumpers. They're trying to get a sense of the thing. People in general have friends around the world. And then there are the splitters who say, no, it's really important that we understand the difference between this kind of, chickadee and this other kind of chickadee, or the beaks of the birds that Darwin studied, the radiation, the finches, the adaptive radiation. We're going to study all the different beaks, and we're going to gain insight by looking at variance and looking at variation and inequality. So we're not looking at the first moment of the distribution, we're looking at the second moment of the distribution. So this is an old issue in the sciences. Much of my work on networks has me as a lumper. I am interested in fundamental points that are generally true in villages around the world. So we've mapped villages in Honduras, in Uganda, in India, in Tanzania, in Sudan. I didn't show you this work, but we've done all of this work mapping these villages, and the mathematical structure of those networks is basically speaking the same, no matter where you go. Notice I said basically speaking, because there is also some differences between them. The gender example is especially poignant, or not poignant, but piquant, when you look, for example, at societies like Saudi Arabia, which don't really encourage or tolerate intersex friendships, right? Men and women aren't supposed to be friends in Saudi Arabia. There's strict gender segregation in that society. And so the question is, well, how might gender affect the structure of networks in Saudi Arabia compared to, let's say, a society which didn't have those kind of cultural norms? And the answer is it does, but fundamentally, it's still very similar. So get back to your question, there are details that matter by age, by sex, by wealth, by all the socially stratifying variables that affect your access to information, where you are in the network, whether the network that you're in is a rich network or a poor network. A poor person in a rich network, in some circumstances, fares better than a poor person in a poor network. In other circumstances, fares worse because of invidious comparisons. So all of those things have been explored by people and a little bit by us. So I'm not giving you a direct answer other than to say that, but generally speaking, the things that interest me are the fact of social influence, the fact of the relevance of social structure, the fact that the things that I've shown you matter. And I recognize that there's also variation by other attributes, but that's not been a primary focus of my work.
You studied them because of men or women.
Oh, well, we lump the women together too. Don't get me wrong. In fact, I'll show you. Hold on. Since you put me on the spot, let me show you. This is a project that we published in Nature in 2012. We had done all this work on the evolutionary origins of social networks and on the genetics of social interaction. And unsurprisingly, some people are gregarious, some people are shy, people vary in their tendency to have friendship. And we thought, well, if it's true that our propensity to friendship is partially encoded in our genes, if we could fly back 10,000 years ago and study the networks of our Pleistocene ancestors, what would those networks look like? Of course, we couldn't do that. So we thought about finding a modern age population that lives like we did in the Pleistocene, in the place we lived in in the Pleistocene, namely the Hadza hunter-gatherers of Tanzania. So we went, one of my postdocs, Corinne Apicella, we made a photographic census of all living adult Hadza. In fact, this was the precursor to the Trellis software I mentioned earlier. We printed this census on big posters. Corinne, who's shown here in the lower right, went to Hadza land. She could speak the language, and she would just wait around Lake Ayasi for like a week for someone to walk by, because you can't make an appointment with a Hadza person. And the person would walk by, and you say, "Excuse me, who are your friends?" And they would point to their friends. You say, "Thank you," and off they go. And you wait another week for the next person to come by. And then you could map the networks of the Hadza, and this is the network of the Hadza women. And so we map the network separately for men and women, and then also jointly. And so we lump the women and lump the men. And here's a lump of women and their social network map here.
Sure, we have a few questions from the chat.
Okay.
So I'll read the first from Jenny. The comment and the question. Comment is absolutely fabulous presentation. Thanks so much.
Thank you.
And the question is, how would social media fit into your theories?
Yeah. So again, this goes back to kind of my intellectual bias, which is I'm interested to the extent that I can in getting to the deepest level of the thing that I can. So I'm interested in sort of the social networks that have existed in a kind of timeless way. Social media is very important, but it's grafted onto the fundamental reality of our social networks. The anecdote that I give for this is, if you could talk to my Greek grandmother, who was born in the southern part of Greece over 100 years ago, she's been dead for 30 years now, about how many friends she had in this little village that she grew up in, the poor girl in the southern part of Greece, she would say, "I have one or two best friends, and there are 4 or 5 of us. girls that hung out together. And if you could have asked my daughter at the same age of 11, my daughter's now 26, but you could ask her that at the same age of 11, when she had an iPhone in her pocket in the 21st century of the United States, she'd give you the same answer. I have 1 or 2 best friends and 4 or 5 of us girls hang out together. So the technology has changed some things, but not others. The fundamental reality that guides the kinds of networks we make doesn't depend on the social networks, on the social media, but the social media exploits certain propensities that we have. So for example, our fascination with the lives of our friends, which is a very primal and ancient thing, is exploited by social media to constantly give us a feed of and seduce us into being interested in what all these people are doing in a way that, in my judgment, is not healthy. So, so we've done some work on social media. I've published 2 or 3 papers on Facebook usage. If you Google Christakis and Facebook, you'll find one paper in the American Journal of Epidemiology on the ill health effects of Facebook usage, and another paper in PNAS on social media interactions and whether they are associated with mortality. So if we look at if you're elderly and you're staying engaged with social media, does that confer some benefits or not, as if you were having face-to-face interactions?
We have time for one more.
And there's one in person here if you want. What I'm happy to do both. It's up to you.
So, a question from Hikma, forgive me if I mispronounce the name. The question is, do you have studies that measure an individual's level of influence? With a follow-up question of how powerful can 1 or 2 people who are like a party host be in these interventions?
So we can do that work, but we haven't done it yet. We could quantify in the experiments we've done what kinds of people are most influential. But what I can say is, if you use the friendship paradox, you find an ensemble of people who are indeed more influential. So that's a kind of quantification. And I can also tell you that in many of these villages, which in these Honduran villages, the villages are ranged in size from 50 to like 800 people, oftentimes you can have as much effect targeting 10 people as targeting all of them. So you really don't need to expend resources to reach everyone in these villages, which I think has significant implications for public health practice. And we're beginning to try to roll out easy-to-use tools to use pair targeting. So other people are trying interventions already, doing your own work, whatever you're doing, you could turbocharge the impact by doing pair targeting. And here's a software tool that will help you enact that. That's what we're hoping to do next. Yes, last question.
This again needs implications. We'll see where it lands, but going back a few slides, suggested that folks have an affinity and actually are better in more associated groups rather than disassociated.
Assortative, not associative.
Sorry, thank you, assortative.
But actually associative also happens. It's a really sad observation about human beings.
We like what
In-group preference, yes.
Similar folks. So first question is about the implications of that, especially with an equity lens.
So
and then second question, and you can choose either one.
Yeah.
Relates to credibility in the use of bots and perceived manipulation.
Yes.
So how to vote for.
So we've done, on the latter thing very quickly, we've done some experiments where we reveal and don't reveal that your alters are bots. So you have 4 humans and 1 bot, or you don't know, they're probably all 5 human. We generally find that actually people are unbothered by being connected to bots, with a proviso that they have the understanding that the bot is beneficent. So if you think the bot is there to help you, then you don't mind. And we find no difference in satisfaction or gameplay when you have a bot or not. And we've done some decryption studies. In fact, in one of the papers I presented in the supplement, there's some analyses. On the first issue, in another whole thing I've done, which I haven't talked about today, I have this, where is it? This book that I'm proud of, that I published in this book. that I published in 2019. And in this book, I talk about the evolutionary origins of a good society. And I talk about 8 features of our social lives that have been shaped by natural selection: friendship, love, learning and teaching. We evolved to teach each other things, which is very rare in the animal kingdom. We take it for granted, but we teach each other stuff, which is uncommon. And mild hierarchy. We live in a hierarchical species. It turns out mild hierarchy is good for us. No hierarchy, groups with no hierarchy don't do well, and groups with extreme hierarchy suffer horribly. So there's a lot of research on this, not so much by my group, but by other scientists, and in-group bias. And it's one of the most depressing observations about the reality of the world, that people prefer the company of people they resemble, and we're a tribal species. Now, one of the things that's interesting is that the boundaries can be arbitrary. In other words, we divide the world into us and them, but the heuristic we use to divide the world into us and them is very flexible, right? So if a whole group of us put on a military uniform that says we're in Team X instead of Team Y, all of a sudden we're like, well, we're all part of Team X. We don't care about any other difference between us, but we care that we're not Y, right? And some of you probably know these famous T-shirt experiments with infants, the minimal group paradigm. It's a classic social psychology body of work. It's really depressing. You can take toddlers, you can randomly assign them to have green and yellow T-shirts. You can test that they understand that the T-shirt color was assigned randomly, that it was not based on desert, whether they deserved it or not. And then you ask them, what should be done with these toys? And they're like, oh, these toys should be given to the green children, not to the evil, bad, naughty yellow children who shouldn't get this toy. Even though they know that you can elicit this, you can just scratch the surface of human beings, and we act in this awful tribalistic way. So it's very depressing to me. I mean, the literature is overwhelming that this is the kind of animal we are. But I'll say 2 things and then I'll shut up. Or maybe 3 things and then I'll shut up. It turns out that there is a lot of theory as to why we evolved to be tribal. And it has to do with that it co-evolved with our capacity, ironically, for cooperation. And I can cultivate that intuition in you in the following way. Imagine you have 1,000 people and you tell them, go out and be nice to everyone in this population. So there are 1,000 people in this population and they're supposed to be nice to each other. And you encounter someone and maybe you're nice to them, maybe you're not, but you have no way of telling them apart from the other 999. You don't know if you'll ever see them again. There's very little impetus to be nice to this person. Maybe they take advantage of you and then you're upset and you're mean to all the other people you interact with. People have done experiments like this. And what happens is you get a tragedy of the commons and cooperation collapses in that population. Now imagine that you take that population of 1,000 people and you divide them into 10 groups of 100 and you give them flags, a purple flag and a green flag and a beige flag and whatever flag. And now you tell them, just be nice to the people that have your color flag. Already you should have the intuition that you're feeling a bit more relaxed. You're like, oh, that's easier. I'll find the person with my color flag and I'll be nice to them. And I can be pretty confident that other people with that flag are using the same heuristic and are going to be nice to me. So it turns out that cooperation, and therefore the levels of cooperation in the population of 1,000 are higher when you divide the group into 10 groups, ironically. So the division, ironically, increases the niceness. Isn't that sad? But it's true, I think. So this is one of the deep ideas about the origins of tribalism in human populations, has to do with the fact that we became tribalistic in order to abet our capacity for cooperation. By the way, the greatest way we are tribal in the smallest group is our friends, our personal friends, right? That's the smallest group of all. And so there was a coevolution of friendship and cooperation. I'm going to close with one metaphor because it relates to a problem that's ascendant in our society today and around the world. We have lots of social problems. So the question is, how can we solve or address some of the problems of tribalism that are so problematic around the world, in our country and in other countries around the world? And evolution provides us a couple of ways out of this conundrum. One relates to some other classic experiments in social psychology, known as the Robbers Cave experiments, for example, which is, and is in all these science fiction movies, the trope when when the aliens invade us, then all human beings band together to fight against the aliens. So one idea is to cultivate a sense of we're all in this together, right? And this is like, for example, we're all Americans. It doesn't matter what kind of American we are, we're all Americans. And this was de Tocqueville's observation about our society, is that our society had this ingrained objective of raising us up to all feel a part of this greater whole, so that the divisions within our society were less relevant. We could all be under this sort of unified ideological framework of we're all Americans. So one way to solve tribalism is to go up a level. But another way to solve tribalism is to go down a level, to the level of the individual. And this was Martin Luther King's solution, right? Martin Luther King says, I look forward to the time when my children are judged by the content of their character rather than the color of their skin, as individuals. So the irony of tribalism is that it lives in this middle range, and that in order to really address it in our country and elsewhere, I think we either have to go up a level, find what unifies us all, like our common humanity, or go down a level and recognize we're each special individual human beings. There's more about that in this book. Thank you very much.
Thank you so much.